Let's go to the lecture. So we're talking about inheritance today. So inheritance is somewhat related to interfaces, but it really is quite different. And so it probably helps you for right now just not to think too much about interfaces. So inheritance is a relationship between actual classes, real genuine classes. Whereas interfaces, there weren't classes. They were this funny thing where they just told you some methods that needed to be implemented. So inheritance is different. You have multiple classes, and we say that some of them may inherit from others. So over here I have some examples. I have a class vehicle, I have a class car, I have a class truck, a class SUV, and so on. And it's clear that cars are like a special case of vehicle. Every car is a vehicle. Every truck is a vehicle. And every sedan is a car. And so you have this hierarchy of specialization. And so that's, in fact, something that happens all the time. We haven't really covered this example, so let me skip past that. This happens quite often when you have layers of classes. And so we say that the more general class, in our example here that would be vehicle, is called the superclass, and the more specialized class, that would be car or truck in this case, would be a subclass. So we would specifically say that car is a subclass of vehicle. And we would say that sedan is a subclass of car. So in the book there's this really kind of dreadful example of different account types, and it's not there to engage the interest of the reader, but just to get the mechanics of inheritance straight. So the issue with inheritance is there's a certain amount of mechanics that one has to do, and so these examples here are designed to show up all of the various syntactical features in an environment that may not be interesting, but at least it's easy to understand. So we have the superclass, the bank account class that we've had since chapter 3. Not a glamorous class either, but simple to understand. We have two subclasses, checking accounts and savings accounts. And so the features of the checking account are that it carries no interest, but it charges fees for transactions that go beyond some minimal number every month. Whereas a savings account gets you some amount of interest that compounds every month. So the idea here is that we want to say all of those are bank accounts, but they're different. They have some behavior that's the same, they have some behavior that differs. And so we want to say that a bank account is the more general case, and the saving and checking accounts are specialized classes. They're subclasses. We want to use this inheritance feature to model that. So all of those classes here have a get balance method, and that one is going to be the same for all of them. To get the balance is no difference depending on which account. Then the bank account, of course, has deposit and withdraw here, and the savings account that has no different way of depositing and withdrawing than a regular bank account, so we simply want to inherit those methods without change. A savings account adds another method, the add interest method, that doesn't make any sense for a checking account or for a general bank account which don't carry interest. And the checking account has a deduct fees method that we will somehow arrange to be called at the end of the month, and it then deducts the monthly fees. And in order to do that job, it needs to know what to deduct. It needs to know how many deposits and withdrawals there were in the preceding month. And so that means that deposit and withdrawal need to be somehow re-implemented in the checking account to do the regular old deposit and withdraw, of course, and then to increment some counter, so that the deduct fees method, when it gets called, that it can look up what that counter is and compute and deduct the fees. So that's the basic setup here. And so you see this very common structure that you have some methods that are reused in the subclasses, some methods are modified in the subclasses, and some methods can just be added in the subclass that don't really apply to the superclass. And so all of those are common operations, and we're going to look at them, how they look like in code. Okay, if I have time later, I'll come to the clicker questions. So Right now, the mechanics here, so whenever you want to use inheritance, it's kind of similar to implementing an interface, but you say extends rather than implements. So when do you say extends? When do you say implements? That part is really simple. When the thing over here is a class, you say extends. When the thing to the right is an interface, you say implement. How do you know whether it's a class or an interface? Yeah, you just look at it, and if it starts out by saying class something, then it's a class, and if it says interface something, it was an interface. So you'll always know which of the two it was. And so depending on whether it's class or interface, you use the keyword extends or implements. Now, when you implemented an interface, you start completely from scratch. The interface has nothing. All it has is some obligation. It says you must implement these methods, but it doesn't give you anything in order to help you out in any way. When you extend a class, it's a little different. The class already has something. It may have instance variables. It may have methods. And so the whole notion, why they call this inheritance, is that you get to inherit them. And unlike real inheritance, you don't even have to wait for the original thing to die. So you get to inherit any instance variables from the superclass that is there, and you get to inherit any methods from the superclass. They're also just there. So in the case of the savings account, I don't need to put in another balance instance variable. I'm already getting one from the superclass. I don't have to implement the get balance method. I already inherited. I don't have to implement deposit and withdraw, since I'm perfectly happy with the versions that I'm inheriting. So all I have to do here is I have to add any new instance variables that don't yet occur in the superclass and add any new methods. And we'll see in a minute how to do that. So here I'll show how to use a savings account and how to use the inherited methods. So here I'm constructing one. Savings account has 10% interest. So this is all very artificial. The interest rate doesn't change over the life of the account. Maybe like a time deposit account. So it has 10% interest. And now I'm going to just call deposit. And I never had to implement deposit. I just get to inherit it. Okay, what do I have to implement? Here are the two methods. Well, I guess it's a field, it's a constructor, and a one method that I need to provide. So I provide an instance variable to hold the interest rate. I provide a constructor that sets it, and then I provide this add interest method that adds the interest. And the implementation of that is here. And the implementation is trivial. You see the constructor just sets the rate. The add interest method just computes the interest using some math. And now look at this line here. So I'm computing the interest by figuring out what's the balance, apply the interest rate. So let's say there was $1,000 in there. My interest rate was 10%. That would be 1,000 times 10 over 100. That would be $100. And then over here, to add the balance, the interest to the balance, I call the deposit method. That does make sense, right? I'm kind of depositing the interest into the bank account, but it seems kind of complicated. Why not just say balance equals balance plus interest? That would seem like a more natural way of doing it, and that's exactly how we've done it before when we implement these methods. But you can't do it. And the reason is that balance is not an accessible field from the savings account. So when you look into here, you'll see there is no balance field. Well, we're not putting it in there because we inherited it, right? It's inherited from bank account. But in bank account, balance was private. That was the whole idea of encapsulation. You want to make all instance variables private. But it seems a little cruel. Right now it means that the savings account can't get at it. Well, it can get at it, of course. It can just use the public methods of the bank account class, such as get balance and deposit. So it doesn't seem to be major hardship in this case. Now, the reason that the privacy is so strictly enforced is there was a time when other programming languages tried it differently. And they said, oh, a subclass should be able to get its hands at the private fields of the superclass. And it didn't work so well. You know, kids would raid the bank accounts of their parents. And worse than that, people would inherit from a superclass just to access the private fields. It's like, you know, you would walk up to someone and say, I'm now your adoptive child. Let me have access to your bank account. And so people would do this in real code, and so designers of programming languages have learned that if it's private, it's got to stay private, and not even the children and grandchildren have any special access rights. It's just the way it is, and it just means that even for those methods of the subclass, they have to use the public interface of the superclass to manipulate the state of the superclass. One gets used to it. Yeah. Yeah. Ah, okay. So let me. What would be better would be over here to put this dot. So if you like, by all means, put this dot here, because that would clearly explain what's going on. I want to have the balance of this account. You're playing with fire, and I'll show in a few slides why. So I don't even want to put it down. Someone will do it if I do. So this dot is perfectly good. It's very reasonable. And it just makes it doubly clear that I want to get the balance of this bank account. So if you like that style, go for it. I talked about that before, that I personally think that's a reasonable thing to do. All right, so back to this picture here. So here you see what a savings account object looks like. It inherits a instance variable from bank account, which, you know, technically speaking, that's an instance variable of bank account. You have no access right to it, but it's still present in every savings account object, even though you can't get at it directly. And then we have our own interest rate. Now, every once in a while, and I think I'm going to have to set this up in BlueJ so you see this. Bank account. What's the damn bank account? Chop. It's not in chapter. Okay. All right. Okay, so back to this savings account. So every once in a while, someone does the following and says they want to get, just do the balance here, and then they say balance plus interest. So this is just what I said before you're not supposed to be doing, and let's try to compile it. And now the compiler says balance has private access in bank account. And as I just said, the remedy is to call get balance over here. But not everyone listens, and every once in a while, someone says, ha. And so now when we compile it, it compiles. And then they think they have defeated the system and move on with their pathetic little lives. So, but what happens now? Yeah, let's give it a try, actually, and make a savings account here. 10% interest. And now let's deposit $1,000 to it. And now when we call get balance, make sure they got there. Here they are. Now we'll add the interest. And now let's see whether the interest made it there. And no, it's still just $1,000. And to see what actually happened, we can inspect this object. And now notice that it has two balance fields. Right? It has the one from itself, and it has the one from the superclass. And so this is not productive, right? You don't want two balance fields. You want one balance field. And so it's very important that you don't make that mistake. But it's an easy mistake to make because it shuts up the compiler, and then you have to find it later during debugging. So let me undo this here for sure. And go through the public interface. Oops, that was one undo too many. Or, like I said before, if you really like, you can put the keyword this here, and that makes it totally clear. So now let's just really quickly look at one of these objects again. Now when I look at it, now there's a single field balance and a field interest rate, and that's the layout that I want. All right. Okay. Come back to this in a minute after I've sown some more confusion. Here's that common error again. You'll find it in the book, and you see here the replicated balance. Bad stuff. All right, so that was kind of the easy part where you just add some methods that didn't exist before. So the savings account simply inherits all of the methods, and it doesn't, and it adds a new one. It gets more complicated if you want to modify the methods from the superclass, like what we'll want to do with the checking account here. So with the checking account, we want to re-implement deposit and withdraw so that it applies that, so that later the deduct fees can do the right thing. So let me just do this here in real time. Checking account. So I want to have this transaction count. So in deposit, I want to increment the transaction count, of course. In withdraw, I want to do the same thing, so apparently it doesn't matter for computing the fees whether it was a deposit or withdrawal. And here I want to say if the transaction count was bigger than whatever the number of free transactions were, then withdraw, I guess, the count minus the free ones. Notice I call withdraw because that's the only way that I can get at the instance field of the superclass. And at this point, I want to set the transaction count to 0 because you don't want to get charged twice. So we've gotten charged for these, and we move on. Oh, I have to define this. Private static final double free, no, int. So. Okay, let's talk about the constructor in a minute. Just for testing, I'll just give us two free transactions here. So do I need a constructor? I guess, no, I don't. I'm lazy about the constructor. Actually, I don't anyway, because by default, an instance variable that's an integer turns to be 0. Right, integers are initialized with 0, floats or doubles are initialized with 0, booleans with false. So why did I need one for the unbounded grid? Yeah, because by default, an array list gets initialized with null, and that would be not so great, right? When you later call a method on the null, it would blow up on you.
Even if it's an array list of doubles?
Yeah, even if it's an array list of doubles, because it is first and foremost an array list, and an array list is an object. So any object gets initialized with null. And an array is technically also an object. It's a kind of a bizarre object, but it is an object. So,
when you construct an array, what measures?
well, if I construct the array, but if I don't construct it, it's null. So there's two levels. There's the reference to the array, and then what's inside the array. And you need to distinguish those two. Yeah, as a total aside, it's nothing to do with this, but I'll say it again because it is important. So that's why I like these pictures. So if you have an array of objects, then it really looks like this. Like, let's say you have an array of location objects. Then you have a reference to the array, which might or might not be null. And then each slot of the array is itself a reference to an object. And any one of those might be null. And pursuing that total aside one more time, because I get complaints sometimes from one of the instructors in 146 who foam at their mouth about this. Consider the following code. What's it print? It'll print null. So you have an array of 10 nulls. That is different from an array of 10 empty strings. An empty string, how would an empty string print? Like this. Oh, it doesn't come out so good on the audio. All right, so so an empty string wouldn't print at all. How do I make myself an array of 10 empty strings?
You just initialize a string array with 10 slots.
Yeah, you really have to have a loop. There's no good other way of doing it. Okay, total aside, but since it came up here. All right. Yeah? Yeah. Yeah, I mean, I meant to write a quote, nothing, and then a double quote. Oh, I could over here, I could say, yes, so I could simply say over here equals empty string, comma, empty string, comma, empty string, comma, and now you know why I didn't do it. Right? I mean, because I can't do the dots, right? So I'd have to write the whole thing. Well, a local variable is never initialized. An instance variable is initialized. But okay, back to your question.
When I'm doing like a local variable and it's just like int blank and then I put a colon, semicolon without actually putting an equal sign.
Okay.
Then I try to put something in that variable later and it says that it hasn't been properly initialized.
All right. So we're getting further and further afield, but that's fine. So what now? The fellow here says, let's say I'm inside main. And now I say int count. And later I say count equals 0. And later I say if count is greater 10, then do something. Right, I'll come to that. So here you see, at this point here, count has not been initialized. Is it 0? No, it's a local variable, and local variables are, by convention, not initialized. So I have to put in the 0 somewhere. I can put it right here, which is the style that I recommend, or you can do it further down. And in this case, everything will be fine. But if for whatever reason I have this if statement here without having the intervening initialization, then the compiler will, of course, complain and say, hey, you've never initialized count. Now, the compiler is not perfectly good at doing that. There's sometimes situation, if there is a mess of whiles and maybe an if in here, you can get yourself in a situation where the compiler is not totally sure whether count was ever initialized or not. Maybe it actually was, but it can't figure it out. And at that point, it might still give you an error and say, I can't guarantee that count was initialized. And so when that happens, the obvious remedy is to just go back here and put in an equals 0 and initialize the darn thing.
Yeah, I was just curious if you could initialize it inside of while statement.
Well, that depends on what scope you want. That's exactly what sometimes happens. So sometimes you have a variable that you first know the value inside the while loop. So you would have a while not done. And now I'm going to read in some number. So int num equals in.nextInt. And that's all fine, but now it turns out you want to use num over here. You say sum equals sum plus num. And now the compiler says you can't do that because num is the scope of num is only inside these braces. So you go and you remove the int from here. And now the compiler says num was never defined. So you go up here and put the definition in here. And now the compiler says, well, maybe it was never initialized.
So it's not sure.
Right. And so in this situation, your only remedy is to put in some reasonable default value in here. And now the compiler is your friend again. Now, in general, this is kind of the only situation when it happens when you follow the rule in the book that says initialize a variable as soon as you declare it. So the book says whenever you declare a local variable, just go ahead and initialize the darn thing. And what if you don't yet know the value? Then you just move the declaration further down. And that rule almost always works, except in this case with the loops. But in general, that rule works very well. Declare the variable as late as possible and declare it only when you are ready to initialize it. And if you've never learned Java before or anywhere else, that's fine. But you may have, if you had a previous course in Java, you may have had an instructor who said you should always put all of your variables all the way on top. Did anyone have an instructor like that? Yeah. And so that gives you a powerful signal, namely that instructor has learned the C language as their first language and has never, ever bothered to learn another language, but simply taken the knowledge from C and carried that forward. In the C language, you had to do it like that. That was the syntax of the C language, and was actually unfortunate. It sometimes meant that people would forget to initialize something, or they would have to fake initialize. So in Java, we have the flexibility of initializing a variable when we need it, and we should take advantage of that flexibility and always initialize a variable. That way you don't ever get into this academic point, what happens if it's not initialized? So you should, when you say int num, you should automatically type the equals. And if you're not ready to do it, move it further down. And in the rare case that, that you're in this situation, just put it as 0 in it. All right, well, back to the originally scheduled program. So here I have my checking account. So have a look at it again. We have a transaction count. We have these free transactions. We increment the transaction count in deposit and withdraw. So let's give it a try. So I'll make myself an account. I will deposit $1,000. And let's see if they got there by calling get balance. Where are my $1,000? I deposited $1,000. Ah, so it called which deposit method? Well, I had a checking account, so it must have called this deposit method. And so all it did is incremented the transaction count. That wasn't so good. So I forgot to update the balance. Oh, balance has private access and bank account. Now what? Oh, I have to call deposit, just like I did last time. Okay, let's try it. So, make myself a checking account. And we'll call deposit. We'll deposit $1,000. And then we'll see if they... What? What is this? Stack Overflow. What? So it went into an infinite loop, and let's see why that is. So it increments the transaction account, and then it calls deposit. Why does it call itself? Well, okay, I'll say this dot. Okay, let's see what happens when I do this dot. I think I may have to... All right, let's have to recompile. Okay, compile, new checking account, deposit $1,000. Get a Stack Overflow. Same thing. Okay, so let's see which method it really calls. So here I'm in my checking account, deposit happens, transaction count gets incremented, and so the call in question is this call. Well, where does this point to? This is a variable. It's a reference. It points to some object. What is the type of this object? Checking account, right? Because, all right, so now the rule is that when you have more than one method that might be called, it picks the method in that's appropriate for this object. Well, what object is it's checking account, so it must call checking account deposit. So it calls itself. And so this is a vexing situation, and to overcome that, they had to introduce a totally new keyword. And that's the keyword called super that says, I do not want the polymorphic dispatch. I specifically want you to break out of that and call the deposit method of the superclass. And so the same thing is going to be true here. All right, so let's first of all try that and see that it does the right thing. So I'm going to deposit $1,000. It didn't crash. $1,000 are in there. We're going to deposit another 1,000. deposit another 1,000, double check that they're there. So now we have 3,000 in there. Now we're going to call deduct fees. It's the end of the month. And now let's see what we have. And now we have $29.99. That makes sense because there were 2 free transactions and we got charged for the 3rd transaction. So it all works. Okay, final look at this code here. Notice, why didn't I have to worry about the withdraw over here? Why didn't I have to say super.withdraw over here?
Because even if it calls the withdrawal in your own function, that withdrawal function this calls the super.
Yeah, so, or to say an easier way, I'm not calling myself. There's no danger of a recursive call here, right? If deduct fees calls withdraw, so what? Kind of so what? Is it really so what? Is there any difference at all between writing withdraw? Well, this would have made a great clicker question. This dot withdraw or super dot withdraw? So now, so which of those 3 should you do? So, well, let's see which one gets called. If I call withdraw, it's the same thing as saying this dot withdraw. And in that case here, it'll call its own withdraw methods. That's the one over here. And that does have the blemish that it updates the transaction count 1 more time. It does it after computing this parameter, so it's not going to be fatal because in the next line it gets set to 0. So in this particular case, something could be said for that it would make a lot of sense to call super.withdraw. I don't really remember what the book does. No, it doesn't matter in this particular case, but you want to ask yourself the question. As a rule of thumb, it's usually more helpful to call this dot withdraw, but in this example, it seems the exact opposite. So the rule of thumb does not apply there. So that's why I'm curious what the book did. The book calls super dot withdraw. All right. So specifically to avoid bumping up the transaction count. All right, and that's all I have for inheritance here. There's a bit more to that. There is a complex way of having one constructor invoke the superclass constructor, and we drew the line at that for 46A. So you're going to be revisiting all of this in 46B, and so the hope is that having seen it once, that the next time it appears to be more natural. And for whatever reason, I wanted you to see both inheritance and implementation of an interface so that both of those get revisited at the beginning of 46B, and by that time it should hopefully have sunk in. I'm not totally fond of either of these of this example with the checking account because it's just so boring. I like the example that was in the lab, so let me talk about that for just a minute and put that in perspective, and then we'll do a couple of clicker questions. We're done. Hang on. So if we quickly go through the lab had this drawable interface, and I really think the drawable interface is a great example of an interface. So when we went through the lab, it started out with this car viewer program that we've had ages ago in Chapter 3. And so in the car component, we draw a car. And the car has a draw method. And then we draw a dog, and the dog has a draw method because that's how you draw shapes. And those draw methods, as they are at the outset of the lab, have nothing to do with each other. They just happen to have the same name. I could have renamed one of them to paint, and as long as I had done that consistently, it would work. But conceptually, they're related. Those are anything that can be drawn should have such a draw method. You want to draw houses in your suburban scene, a ball, a kid, a car running over them. So you want to, these are all just drawable things. These are all things that can be drawn. And so there's this commonality between these otherwise disparate things. And that's where now you can model this in one of two ways. You can say you have an interface drawable, and then you have car and ball and so on. Implement that interface. And that works beautifully. That way, any number of classes can choose to implement that interface. And then in your code, as you've seen in the lab, you can now have an array list of drawables. And then you just pack things into that array list, and then you can make all of the drawing with a single loop. That's where the first part of that lab drew you at. So why use should one use an interface here? Or the other option is one could use a superclass. So one could make drawable into a superclass and then have house and car inherit from it. And so that would be another option of modeling the same thing. What's better?
Probably interfaces, you won't be inheriting any specific values.
Yeah, so in this case, that's exactly right. There's nothing specific there's no service from Drawable that does us any good. There's nothing that Drawable has to offer in terms of helping us out in any way. All it does is it applies a single method, and it doesn't even know how to do it itself. So that's the classic situation for an interface, where you just have the name of a method, and that's all that you want to decide upon. So since there's absolutely nothing useful in there, that's the right choice. And the interface has a great advantage in that a class can implement as many interfaces as it likes, but it can only extend one superclass. So before you get into inheritance and superclasses, you want to make sure that this is really the one true parent. And otherwise, by default, you should always choose interfaces, which is why in the book, the interface chapter comes before inheritance, because interfaces are actually more useful. Yes? Oh, in fact, I think it does happen. Does it happen in the lab? Let's see. It might have. Yes, it does happen. Later on, we have a movable interface. This is actually a great lab. And in that case, you can say that class car implements drawable and movable. And that happens once in a blue moon. It's not a terrifically common thing, but in this case, it actually made some amount of sense to have it like that. So the inheritance example here, if you've gotten to it, or you may get to it in your last session, is a lot more artificial. So we have a clock superclass. I need some room here. Good enough. And so the clock provides some services. The major service that it provides is it draws the hands of the clock in the right place. And then the subclass was the world clock. That was just like a clock, except it should work in any old time zone. And so world clock then draws itself in some other time zone by just adjusting, well, presumably the minutes are the same, by just adjusting the position of the hour hand. And it inherits the basic services from clock, that it knows how to draw the circumference, that it knows how to position the hands. So it inherits a whole bunch of behavior, and so that's a reasonable thing to do. And it just modifies a little bit of behavior when you set the time it needs to do that adjustment by those few hours. So we're taking the basic clock class, and we just want to make an itty-bitty change to it, and that's where inheritance comes in handy. And so when you contrast those two things, the drawable, movable, those are like very generic concepts. That's where the interface is the right solution. And here we're taking a big fat class that already has some interesting behavior. Now we want to make a small change to it. That's where inheritance comes in. That kind of gives you a good mental image when to use one or the other. All right, well, since I have a few more minutes, I will run one of the leftover clicker questions. All right, let's do number 3 here. That way at least we'll get some attendance. Piazza. Okay, so where was the savings account classic? Again, let me pull it up. So we have this class here. And the question was, which of these methods can you apply to an object of class savings account? Have no results? Huh? Okay, it hates me. Oh, here we go. All right, yes, so yes, we see a whole bunch of results here. And all right, so I'm not entirely sure what would motivate you to say the first 2. I just tossed them in there, but apparently a couple of people did. Would anyone care to say what made them choose this?
Close your eyes and click.
All right, yeah, maybe. So I think there's a rational reason why someone might choose 3, and that was when you look at the savings account class, that's the only method there is, right? But of course the right answer is 4 because we inherit these ones here, and you can use the methods that you inherit, and we define this one here. And that is, what most people did get. All right, on Monday, there's not going to be any new material. Instead, I will talk about the final, and I will go through as many old homework and practice questions and exam questions as you want to see. All right, so I'll see you Monday.